Thank you, Andrew. So nice. So next we have a quantum expert. Now finally, it was very hard for us to get one from MIT. So now we have Eleanor. She studied at quantum physics at UCL, and then you are researcher at MIT, and then later at Harvard. And now she's trying to give us an idea about the hack and where the field of quantum is moving. Please come.
Cool, thank you so much.
And she's a friend of Serge, which people know
yes.
Serge is. I forgot the most important part.
Yeah.
Yes.
It's fine. There's no.
Amazing. Yes, absolutely. So, and you guys had a quantum day yesterday as well. Do you have some open questions from that day yesterday? Or what we can do is, whilst you think about it, so I think, hopefully we can just take this time to actually answer some questions about quantum computing. And I'll lob up a couple of slides, but really I think the more interesting thing for you guys is if you have questions, ask. Okay, so yeah, what are the kind of the main areas, let's say, that quantum can make a difference in? Yes, cryptography. Yes, great. Okay, you nailed it already. The thing is, and more?
I think just biological molecular structure.
Yes, absolutely. And I would even categorize that maybe in simulation, unless you're thinking of kind of optimization. And the thing is, with optimization is there's this kind of Harrow-Hassard and Lloyd algorithm, but the really complicated thing with optimization, so we have cryptography, simulation, and those what kind of speed ups do they have compared to a classical computer? Why would you run that on a quantum computer? Why not do it with AI, or why not do it with a classical computer? Yeah, because exactly, it's polynomial when you run it on the quantum computer. So what does that mean? It's kind of like, it means that when you try and solve a quantum problem, do you know examples of quantum problems that you would run? Like what kind of quantum simulation? So you said molecules, in fact, didn't you? Yeah, so the way that you get protein binding ligand events and all of these things, or like batteries, another great example of, your phone runs out of battery, my computer runs out of battery, super annoying. How do we make better batteries? This is actually really, really tough. Classically, we actually have to make a material, try it out, try and do trial and error, try and make another material, try it out again. And so this is a very lengthy process, and you can see that it's a kind of like a random walk, and it's a bit like a gradient descent algorithm, but there's not going to be any bounds on actually figuring that out. And so, okay, so now we have to wrap up all of the boxes that we just opened. So I'm now actually an assistant professor of quantum computing at King's College London, but I hang out because I'm still at HKS.
No, sorry.
But yeah, no, thank you. But I mean, what you were saying was also correct. And Serge, yay. And so, okay, so we're gonna close the boxes that we've just opened, but just to kind of recap, visually, you've got like discovery of molecules, and in here you can also have, batteries. That's what we were just talking about. And to simulate a battery, let's just go back to that question just now. How would how do we want to do that? We want to do that from first principles. We want to do, there's an atom here. This atom has an electron on it. There's another atom next to it. It also has an electron. There's another atom next to it, and so on. And what is the battery supposed to do? It's supposed to store current and be able to convey electricity. Electricity is just electrons moving in a material. So basically, best thing you could do to come up with a new battery material is simulate it from first principles, where you have the atomistic modeling of the atom, which creates a potential for the electron to sit in, another atom, another potential, another electron, another atom, another potential, and then decide on what kind of atoms you should be putting in that battery for it to store the most electrons, or for it to have the best current flow. That makes sense, right? Yeah. And so and what you were saying, what's your name? Isabella. What Isabella was saying is that actually that is a polynomial time algorithm on a quantum computer. So it means, actually I think I have a slide on this. Okay, now we start with the discussion, so it's going to be a little bit of the shop. But But basically, if you imagine you have this battery, you've got the atoms in the battery. On a classical computer, it's an exponentially sizing problem, and on a quantum computer, we'll see it's a polynomial sizing problem. So it means if you have 20 atoms in your battery, the classical computer will take, for example, hours to optimize that system and tell you what is the best material to make your battery out of. But 20 atoms is a tiny, tiny battery. That's not even really a battery at all. So actually, that's not a useful result for us. And now if you make your battery bigger by like, say 200 atoms, still not really a battery, maybe it'll, for example, take longer than the age of the universe, for example. So that's why we can't do quantum simulation on a classical computer. We can't do that first principles quantum simulation. We can't from first principles, but we can do that on a quantum computer because it scales polynomially. So it's really like, basically, if you have classically, you have one atom, it takes 1 unit of time. 2 atoms, it takes 1 to the 2 units of time. Or sorry, 2 to the number of atoms, because you have 2 different. Okay, now we're going to go. It's going to be really complicated. I'm going to try and explain exponential scaling. Let's just take it visually because we don't have that much time. And okay, now let's go back to going through the talk. Okay, so we had quantum simulation and cryptography. So what can quantum computers do? They can break cryptography. So basically, you can Shor's algorithm, the way that numbers are encoded, RSA cryptography, or the way that it's like you send a key, and the way that this key is sent is by multiplying 2 numbers together, but you can't actually factor a number very easily, and Shor's algorithm can do that. So you can break the secrets. And then, QKD gives you a way to kind of communicate securely again. And quantum sensing gives you a way to kind of create new measurements of systems. And what this allows you to do is basically, any country or nation, by the way, who'll have a quantum computer first will be able to generate so many patents and so much IP that they'll kind of be able to exert a form of commercial dominance over the rest of the world. Kind of interesting. It's often not really thought about like that in quite so much of a way. And if we think about what the different countries are. Oh, I think you have it inverted. How do I?
So like this is fine. You can see this. We tried already to solve it.
Oh, you tried to solve it? Okay, thanks. Okay, so let me edit my slides then. So if you.
Sorry.
Oh yeah, and now it's gone. Okay, so it's tiny, isn't it? But okay, so we made this emerging tech indicator with the Belfer Center at HKS, and you can see that in emerging tech in general, it looks like the US is in the lead. But if you now consider specifically quantum, you have that the US, China, and Europe are all kind of within an error bar of each other. It's very difficult to also quantify these numbers, so these error bars are actually pretty big. And so it's not clear in quantum.
What is the y-axis then?
Oh, so it's like it quantifies the amount that the nation has invested, the number of publications that they've done, the amount that they're leading in cryptography, communication, sensing, and the kind of IP landscape, the number of patents that they've generated. So it's a sort of like total sum of all the different strengths within that country. And so yeah, you can see that if you add up, in general, all the data that we can get on quantum, it looks like the US is doing a good job, but so is China and so is Europe. Just to add some kind of urgency in there about things. And so there's different kinds of hardware, but I don't know which areas you guys are most interested in. I would maybe bring up, yeah. Oh, so I haven't put photonics on here because I don't think that it's going to win, and they haven't done any proofs so far. So they're very, very closed in their research, and they're encountering also lots of challenges. So they've kind of overcome some barriers, but also they have so many open problems left. Like basically a photon it's very well isolated from the environment. So they're going to have very high fidelity gates, but at the same time, the fact that it's so well isolated means that it's hard to actually get them to interact in the first place. So there's loads, and the state of Chicago invested loads and loads and loads of money in it. But these are the platforms that I think, well, these are the platforms which, not even I think, these are the platforms that have already made demonstrations of error correction. So, you have a lot of noise in quantum hardware. And so, for example, if what's the example of a qubit? Yes, an electron, exactly. So an electron on an atom could be a qubit. How do you control it? Like to do a 1 or 2 qubit gate? You zap it with light. And light is just an part on the electromagnetic spectrum. So it means you control the qubit with electromagnetic radiation. If I stand with my phone next to the quantum computer that's on the table, my phone is emitting all the time electromagnetic radiation. It is going to maybe interfere a bit, for example, with the electron. That's a little bit imagery because it might not be the right wavelength, but you get the idea. The whole if there's a tube going outside, it might shake the table. That will also interfere with the quantum computer. So they're very noisy devices, and you need to kind of isolate it as much as you can. But there's always also going to be mistakes, and that's why we introduce the concept of error correction. We say, hey, if I can kind of decide to have, if I can quantify that I have this little noise and it's quite well isolated, maybe I can make a majority vote and say, I'm going to consider that there's going to be this many physical qubits, so this many electrons, and if they all have the same state, I'm going to take that to be the state of the logical qubit. Okay. So I just want to show you this because this is the quantum economic advantage calculator that we made with a team of people over at MIT and Accenture, and it actually indicates I should have asked you, but when do you guys think that cryptography will be broken by quantum computers? Today? Yes, today. Damn, we are outdated already on our quantum economics. This actually shows that before around 2030, cryptography will already be broken. And countries are often only migrating in timelines of say 2032, and signals are already migrated to post-quantum cryptography. But there's a lot of discussion in the policy land and in governments of when do we actually migrate to post-quantum cryptography? And often the recommendation right now of the NSA is to migrate to a cryptography which is still classical. So instead of factoring a 2048-bit integer, they're like, hey, just make your integer even bigger and the quantum computer will take a little bit longer to factor it. So that's one approach. Or say they chose a different classical algorithm that the quantum computers don't know how to solve yet. That's often called post-quantum cryptography. But just in 2020, must have been 2024, there was Yilei Chen, who was at Tsinghua in China, and he made a whole algorithm for breaking lattice-based cryptography, which we don't know how to break yet with a quantum computer. And he said, hey, I've got a quantum algorithm to do that. And the whole quantum community was I remember the meetings that we had with the quantum group at MIT, no one could figure out where, if there was an error with this thing. And it took the whole quantum community 9 days to figure out that there was a tiny error in the one assumption on step 9. So I'm just telling that story to say, actually, it's, I don't know if I quite believe, I believe in academic progress being really fast. So I don't know if I think it's a great idea to do post-quantum cryptography with just a different classical protocol that we just didn't come up with a quantum algorithm yet. And when we have access to quantum communications, which would make it fully quantum secure. So this is a very cool online tool, by the way, because it allows you to choose your platform and choose your algorithm and decide and find out what company will solve the algorithm at what date. Who thinks that that is cool? Great. We have the guy who made this tool in the room, which is crazy, Hans Gulach at the back here. So if you're interested in that tool, chat with Hans. It is actually pretty nice, and it has also influenced a lot of people. Okay, so just a little thing to finish off. So it's also happening super soon, quantum simulation, also happening very, very, very soon. And in order to do quantum simulation, you have like, you know, you want to figure out how those electrons are interacting with each other, for example, so you map an electron to a qubit, or you figure out, you want to look at photosynthesis, so you want to know how does light hit the leaf and it like flips an electron up, and then that electron moves along, you know, that excitation, that energy quanta, it moves along the leaf across this like electronics network to the photosynthesis processing center. And so you're always actually, what you're doing in quantum simulation is you're always mapping the behavior of light, which we call bosons, and electrons, which we call fermions. And actually bosons can also be things like vibrations. And actually fermions can also be things like, you know, neutrons. And so there's these categories, bosons, for example, light, or fermions, for example, electrons, and you map it to qubits. And this is really expensive, and I'm interested, and I'm very happy to explain this in more depth to anyone who's interested. But what we've been doing with teams, and which got me even my job and stuff, is that we basically proposed to make a new age quantum computer. Instead of using qubits in your circuit, you directly use light, and in fact, you know, it's like optical computing. Yes, it's somewhat like optical computing. So like, you know, you were asking about photonic quantum computer earlier. There, the qubits are made of photons, which is light. But there, it would be very, very hard to get the photons to interact with a qubit degree of freedom. And if you only have a boson, it's a linear oscillator, and you need to add some nonlinearity. So often you actually really need this kind of, you need to couple the boson with a qubit. But yes, basically it's related. It's not the same model as what we call but you know, if you take superconducting qubits, you basically have a cavity where the Josephson junction, like superconducting qubit, is on a chip and it's interacting with a microwave mode in the cavity. That microwave is literally already a photon of light. And so we could make this model, this new age model of quantum computing in existing hardware platforms. So to complete what I just wanted to finish on, yeah, it would be actually helpful in some way to have some slides at this point, but
You're getting there. It's connected again.
But so and so the idea is, hey, let's use these platforms that are being developed anyway, say it's for example in, you know, Yale or whatever, and use them differently, not just for their qubit degree of freedom, because qubits are very simple there, right? They're really just two-level systems. But we're trying to map these complicated phenomenon of nature, thank you, onto that instead. And so, oh yeah, that's right, you still can't see.
Is it any coincidence that the Olympics are in 2030 in France? Sorry, I just saw France.
Oh, where?
2030 is a timeline.
Oh yeah, 2030 I think is when the first quantum computer will break our cryptography standards.
Okay.
Yeah.
Sorry. Well,
Yeah.
Happened to be in France. So I didn't know
Oh yeah. No, I mean France was setting up the whole of the cold atom architecture, which is being used at QERA down the road. So yeah.
Sorry, you just mentioned like some sort of
thing to think about.
nation state interest in like keeping like cryptography, I guess, lower than, you know, sort of like what are your concerns with that? Because like, you know, obviously there's the intelligence of gathering systems.
Yeah. So I actually think it's something I was thinking about last week is it's interesting because you think, for example, when you're a quantum company and you think you're about to break cryptography, you might think, I want to keep all my secrets to myself to have an advantage. But if they are not open enough with how close they are to breaking cryptography, I think that, you know, the scientists and the CEOs of those companies who want to keep the secret to get this advantage, they still want to live in a world which functions. But if they break, you know, if they declare too soon, too close to the fact that they're going to break cryptography, then they can basically scare policymakers, and they will make some like bad policy decisions out of angst and shock. And also, no one knows what like very powerful people who are very powerful people will do when they get told that someone can read their secrets. They're very powerful people. They can annex or do anything they like with that company, however much we think we're all like free and whatever. So I think there's actually a strong case to be made for openness, which has also, out of interest, been the standard in cryptography for years and years and years. Why is it the standard in cryptography? Because it's actually, if you want to make a strong safety system, you're better to publish it openly so that people can check whether it's safe or not. And that's, like Signal. And so, but I mean, people are migrating so fast that it's a bit like, it's hard to know exactly what the impact will be when this is. Okay, so let me just finish very quickly what my pitch is to you guys is, so we can make this novel kind of quantum computer. It's had a lot of success when we've presented it to the worldwide community in quantum, and people want to try and implement this now on hardware. But the thing is, you need to basically make a model of photosynthesis or your battery, whatever you're going to do. It's acting on fermions and bosons, as we were saying, like the light and the electrons and stuff. And it has this kind of, this is how it evolves in time. That's how the model evolves in time of photosynthesis. But now we want to kind of apply it to existing quantum computing hardware, where we have qubits. And usually the microwave modes are controlling the qubits, but we want to include them into the calculation and make a super powerful quantum computer. And so we need to make this step of breaking down this evolution into this specific gate connectivity. But that's actually a problem that, like, I spent much of my postdoc trying to just figure this out. Here is actually one of my calculations. You start from this kind of qubit-controlled boson moving, and so we can explain, if anyone is interested, what these different what the symbols are. But basically, you have a photon, and it hops to a different side, and it flips the spin of a qubit. That's X on the qubit, and so it's got this multi-mode and qubit gate. Modes are just other words for boson. And here I had to do loads of maths and calculations and come up and test loads of different options for how we could break this down into a set of native operations on the qubit hardware quantum computer. And in a different paper, that was published in IEEE, we actually made what we called a symbolic Hamiltonian compiler, but it was a little bit wishful thinking. Really what we did is we just made like containers, and we made like a structure which is available on GitHub, where you kind of input the Hamiltonian, that's the big model of the general system in nature. You break it down onto qubit gates. So you parse it, and then you transform it into qubit boson gates, and then you generate the new output to run on your quantum computer. But really, here, every single time, we just put stuff that I'd already figured out, like equations that we'd already figured out. Like this one, we know, because it took ages for someone to work through it. And I would love to, give you guys the GitHub, and you get to here, and you replace this whole step, which is known rules, with an AI that knows how to symbolically do the maths on these qubit boson operators, and just generates itself loads of options and tests them to see whether it's correct. And then you come up with the actual circuit that you can run on the device at the end. And I would say this is like an academic, the motivation for you guys is more like, we write an academic paper about it at the end, or like another conference proceeding or whatever it is you guys are interested in. So yeah, if you're interested in this, that's cool. We can chat about it. And I think I'm probably at time. And so I have to go now to do writing lots of grants, but basically I would